Saturation. This describes how much of something can dissolve. If you can still dissolve more of something, let's say I'm making tea and I want it to be sweeter. As long as I can dissolve more sugar in there, it's unsaturated. There's still more sugar that can dissolve. If I've dissolved as much sugar as can possibly be dissolved, and no more can theoretically dissolve, I now have a saturated solution. It contains the absolute maximum amount of solute that can dissolve in that solvent at that temperature. If I get even more than that to dissolve, I get a supersaturated solution, which is kinetically unstable. More than the maximum has dissolved, and it desperately wants to precipitate out. It just needs a place to start precipitating. And those end up with some cool reactions that we'll look at in a second. So unsaturated solutions, they have less than the maximum amount of solute dissolved, and they can dissolve more. Saturated solutions have the maximum amount dissolved and cannot dissolve anymore. And supersaturated solutions actually contain more than should be theoretically allowed. And so it desperately wants to precipitate out. Sodium acetate is used in a lot of these. So let's look at some YouTube videos. There's 2 commercials now. Now here we have a supersaturated solution. It doesn't look like it, but actually more than the theoretical amount of sodium acetate has dissolved in there. And it wants to precipitate out really badly. It just needs a place to get started. So he's going to add a seed crystal. And if you just add one little bitty crystal, that gives it a precipitation start point, and all of the excess will precipitate out. So there he goes. And let's watch that again. He's just going to put one tiny crystal in there, but that gives it a place to start precipitating, and you can see tons of it precipitate out because it's actually supersaturated. And it desperately wants to precipitate out, it just doesn't have a place to get started. They put one crystal in, and then boom, you watch the whole thing crash out. Because it was supersaturated. It wanted to precipitate. It just didn't have a place to get started. You can see the same effect with supercooled water. So you have this liquid water. They use Fiji water a lot for these demonstrations because it's actually super pure. And so it works well for this. For this to work, it's got to be really pure water. Because the water, you're freezing it to -20, so it's actually way below its freezing point. But if there's no place for the crystallization to start, it'll stay liquid. And now we have what we call supercooled water. Because it's still liquid water, even though it's way colder than the freezing point, because it didn't have a place to start the freezing process. So they pull the water out. The water's now -20, though you can see it's still a liquid in there. But all it takes is one atom for it to start crystallizing around. So they're going to smack the bottle to bust off one atom of plastic so that the water starts crystallizing around it. And there it goes, and you see the whole thing freeze into a solid. And that's because it's way below the freezing point. You just needed a place to get started in the crystallization process. So supersaturated solutions, supercooled solutions, they're kinetically unstable. Because like that water desperately wanted to freeze, it just needed a place to get started. Or like the supersaturated solution, it wanted to precipitate out, it just needed a place to get started. And once it has that place, it happens very quickly. With super cooled water, you worry about that on airplanes, because all of a sudden one of your instruments can freeze over in a second because it was super cooled water, so it just flash freezes onto the plane, and then boom, you don't have an instrument that you needed. So that is super cooled water. Any questions on that? Sodium acetate is used a lot. Of all the compounds, this one supersaturates the easiest. And so if you're doing a demonstration, it's the easiest to set this up with sodium acetate. And you can buy reusable hand warmers. There's a little metal disc in there. You click the metal disc, it pops a metal atom off, and all the sodium acetate precipitates around it. That releases a lot of heat. Then you can recharge it by throwing it into boiling water. And that metal atom redeposits on the metal disc, and then you can do it again. And so reusable hand warmers use this theory. Will a solution prepared by adding 9 grams of potassium chloride to 20 grams of water be saturated or unsaturated? Well, 34 grams of potassium chloride dissolves in 100 grams of water. We have 5 times less than that. So what's 34 divided by 5? It'd be like 6 point something. So only 6.8 would dissolve, and then the rest would fall to the bottom of your beaker, and it would be a saturated solution. Don't ever assume it's supersaturated unless the problem specifically tells you it all dissolved. Notice here, it just says you added this to the water. It does not say it all dissolved. Supersaturation is very rare and unusual. And so if something is supersaturated, the problem will tell you specifically that it all dissolved. Usually when you add too much of something, like let's say I'm making my super sweet Kool-Aid, even if I hit the saturation point of water, the sugar will just fall to the bottom and start collecting at the bottom of my Kool-Aid. That's more normal. You saturate a solution, and then any additional that you put in just falls to the bottom as a solid. Effective particle size. Who here has ever had a powdered donut? Feels different on your lips. Powdered sugar, the particles of sugar are way smaller than in granular sugar. And that means they dissolve a lot faster. The smaller the particle is, the more surface area you have for the same amount of solid, the faster it can react with a solvent. And they show this with these crystals. Let's say I have a sugar cube, 1 centimeter by 1 centimeter by 1 centimeter. I put this in my tea. There's only 6 square centimeters of surface area. Now, let's say I break up my sugar cube into 1,000 baby cubes that are 0.1 centimeters. So it's 10 cubes high, 10 cubes wide, 10 cubes deep. I have 10 times 10 times 10. I have 1,000 mini cubes. The overall amount of sugar is the same still. It's 1 cubic centimeter of sugar. However, now my surface area is 10 times more. So as I made smaller particles, because before these inside parts were not getting exposed to water, just the outside was. So when you break the particle up, now I have the same amount of sugar, but 10 times more surface area. So if I broke this big cube into 1,000,000 smaller cubes, I get 100 times the surface area. If I broke it into 1,000,000,000 cubes, I get 1,000 times the surface area. And so as you make the particles smaller, you have more and more surface area. It can react faster. And so powdered sugar will dissolve faster than a sugar cube because it's the same amount of sugar, but with the powdered sugar, there's a lot more surface area for the water to connect to and start dissolving. So the smaller the crystal size, the faster something will dissolve. Effective temperature. As you make something hotter, solids will dissolve faster and more of it will dissolve. And like we said earlier, gases will actually escape. And if you want to try that out at home, try cooking a bottle of Coca-Cola and see what happens. And you will get the absolute flattest pop ever. In fact, just keep cooking it, reduce it down to a syrup, and now you have cola syrup, which they sell at pharmacies to help with upset stomachs. Cola syrup is soothing for upset Effective solute concentration. Things dissolve the fastest when nothing is dissolved yet. Imagine the solvent having pockets that the sugar can go into. When you first put the sugar in, all those pockets are empty, and so it starts dissolving really fast. But as those pockets fill up, there's less and less and less space for the sugar to dissolve into, and so it starts dissolving slower and slower and slower and slower, because the sugars have to wait for a pocket to come by to dissolve it. Then at some point, you get your final saturated solution, when all the pockets are full and no more can dissolve. You can keep adding sugar in, but no more will dissolve because that water can't hold any more sugar. All the pockets are taken up. So the dissolving rate is highest when there's nothing dissolved. As the solution gets more and more closer to being saturated, dissolving slows down. All right. The purpose of dissolving reactants in a solution is to allow them to react, like you saw with the luminol chemical reaction. You can put all the powders together, but nothing happens. Because in the solid form, those electrons are bound, and they're not free to do anything. When you dissolve them in water, all of a sudden they're solvated, and their electrons are free to do chemistry, and now you get a chemical reaction. Most chemical reactions require solvation. And so if I just put potassium chloride and silver nitrate together, nothing happens. But if I dissolve them, aqueous means they're dissolved in water. If I dissolve them and add them, now I will have an instantaneous chemical reaction. And I'll get silver chloride as a precipitate.